Hello everyone, and welcome back to Snoozing Scientist. Tonight, we're going to drift into one of the most fascinating and mysterious ideas in modern science, the possibility that our universe may not be the only one that exists. But before we begin our journey, take a moment to get comfortable. Let your shoulders relax, allow your breathing to slow, and settle in as we gently explore the strange and beautiful ideas that scientists have proposed about the nature of reality. And as always, if you feel like it, leave a comment below telling us where you're listening from tonight. It's always amazing to see people from all over the world gathering here, quietly exploring the universe together. Now, let's begin. Imagine for a moment that reality is much larger than we have ever suspected. For most of human history, people believed that the Earth was the center of everything. The sky seemed to revolve around our world, and the stars appeared as distant lights scattered across a vast dome overhead. But over time, science slowly changed that picture. We discovered that Earth is only one planet orbiting an ordinary star. Then we learned that our Sun is just one of hundreds of billions of stars inside the Milky Way galaxy. Later still, astronomers revealed that the Milky Way itself is only one galaxy among hundreds of billions spread across the observable universe. With every discovery, the universe grew larger. And now, some scientists believe that even our vast universe might be only one small part of something much bigger. This idea is known as the multiverse, the possibility that many universes may exist, each with its own space, time, and physical laws. At first, this idea may sound like pure science fiction. But surprisingly, several serious scientific theories suggest that multiple universes might naturally arise from the laws of physics themselves. To understand how this idea emerged, we need to go back to the early moments of our own universe. Nearly 14 billion years ago, the universe began with the event we now call the Big Bang. In the earliest fraction of a second after this moment, space itself expanded incredibly rapidly in a process known as cosmic inflation. During this brief but dramatic period, the universe grew from a tiny region smaller than an atom to something vastly larger in an incredibly short time. Some physicists believe that inflation may not have happened just once. Instead, inflation might occur repeatedly, producing many separate regions of space that expand into their own universes. In this picture, our universe would be only one bubble among countless others floating within a much larger cosmic structure. Each of these bubbles could contain its own galaxies, stars, and planets. But they might not all be identical. The laws of physics in each universe could vary slightly. Some universes might have stronger gravity, different particle masses, or entirely different physical constants. In many of these universes, life might never form. But in a few rare ones, like ours, the conditions might be just right for stars, planets, and living organisms to exist. In this way, the multiverse could help explain one of the most curious features of our own universe. The physical constants that govern our world appear to be remarkably balanced. Gravity is strong enough to pull matter together into stars and galaxies, but not so strong that the universe collapses immediately. The electromagnetic force allows atoms to form stable molecules. The nuclear forces inside atomic nuclei hold matter together without tearing it apart. If any of these constants were even slightly different, the universe might look very different from the one we observe. Stars might never form. Atoms might never exist. And life as we know it might never arise. In a multiverse, however, this delicate balance might not be surprising at all. If many universes exist with different physical properties, then observers would naturally appear only in those rare universes where the conditions allow life to emerge. Our universe might simply be one of the few places where everything happened to line up just right. Another fascinating idea about parallel universes comes from quantum mechanics, the strange set of physical laws that govern the behavior of particles at extremely small scales. In the quantum world, particles do not always behave in predictable ways. Instead, they exist in states of probability, where multiple outcomes are possible until an observation is made. One interpretation of quantum mechanics suggests something extraordinary. Every time a quantum event occurs with multiple possible outcomes, the universe may split into separate branches. In one branch, one outcome occurs. In another branch, a different outcome unfolds. This concept is often called the many worlds interpretation. According to this idea, countless versions of reality might exist simultaneously, each representing a different path that events could have taken. In one universe, perhaps a star formed slightly differently billions of years ago. In another, perhaps Earth developed under slightly altered conditions. In still another, history itself may have unfolded in ways completely unfamiliar to us. These parallel worlds would exist alongside our own, separated not by distance in space but by different paths through possibility. Of course, these other universes, if they exist, would be incredibly difficult to detect. They might lie beyond the limits of our observable universe, forever hidden behind regions of space expanding faster than light can travel. Or they might exist in dimensions beyond the ones we directly experience. Some theoretical models of physics suggest that the universe may contain additional spatial dimensions beyond the familiar three of length, width, and height. These extra dimensions might be curled up at incredibly small scales, invisible to our everyday perception. Within these hidden dimensions, entire universes might exist, separated from our own by distances measured not in kilometers, but in entirely different geometries of space. Even though these ideas remain speculative, they have inspired scientists to search for subtle clues that might reveal whether our universe is part of something larger. Some researchers study patterns in the cosmic microwave background, the faint afterglow of the Big Bang, looking for unusual features that might hint at interactions between universes. Others explore the mathematics of string theory, which suggests that many different types of universes could arise naturally from the fundamental structure of reality. So far, no direct evidence for parallel universes has been found. But the idea continues to intrigue physicists because it emerges naturally from several of our most advanced theories. And perhaps that is part of what makes science so beautiful. Sometimes the universe is stranger than we ever expected. Sometimes the equations that describe reality lead us toward ideas so vast that they stretch the limits of imagination. The possibility of parallel universes reminds us that the cosmos may be far more complex than we currently understand. Our universe, filled with galaxies, stars, and worlds, may be only one small region within a much greater cosmic landscape. And somewhere beyond the boundaries of our observable sky, other universes may exist. Universes with different histories, different stars, different possibilities. For now, these worlds remain hidden from our view. But as scientists continue exploring the deepest questions about space, time, and the nature of reality, the idea of the multiverse remains one of the most intriguing possibilities ever imagined. And as we continue our journey tonight, we'll explore more of these strange and beautiful ideas about parallel universes, how they might form, how they might differ from our own, and what they might reveal about the true nature of the cosmos. As we continue our quiet journey through this idea, it helps to slow down for a moment and imagine what a universe actually is. When we say the universe, we usually mean everything that exists, all space, all time, every star, every galaxy, every atom. It feels like the largest thing that could possibly be imagined. And yet, in some scientific models, what we call the universe may only be a small region inside something much larger. Picture an enormous ocean stretching endlessly in every direction. Across the surface of that ocean, bubbles begin to form. Each bubble grows, expands, and develops its own internal space. Inside each bubble, galaxies form, stars ignite, and planets slowly gather from clouds of dust. Each bubble would feel like a complete universe to the observers inside it. But from a much larger perspective, it would simply be one bubble among many. This is one way scientists imagine the inflationary multiverse. According to this idea, space itself may still be expanding in regions far beyond what we can observe. New universes could continue forming as separate pockets of space inflate and drift away from one another, each developing its own cosmic history. The distance between these universes might be so immense that light could never travel between them. From our point of view, they would be forever unreachable. But mathematically, they might still exist. Another fascinating possibility arises from the strange geometry of space itself. In our everyday experience, space appears smooth and continuous. We move through 3 dimensions without noticing anything unusual. But at incredibly tiny scales, far smaller than atoms, space may behave in very different ways. Some theories suggest that the universe may contain extra dimensions hidden beneath the surface of reality. These dimensions would not stretch out across large distances like the ones we see around us. Instead, they might be tightly curled into incredibly small shapes, woven into the structure of space itself. If this is true, it raises an interesting possibility. Our universe might exist on a kind of 3-dimensional surface floating within a higher dimensional space. Physicists sometimes refer to this concept as a brane, short for membrane. Other universes might exist on nearby branes, separated from ours by tiny distances in these hidden dimensions. In such a picture, entire universes could exist right beside us, not far away in space, but slightly offset within higher dimensions of reality. We would never notice them directly because all the particles and forces we experience are confined to our own brain. Yet gravity, which may extend through these hidden dimensions, might carry faint traces of their presence. Some physicists have even proposed experiments designed to detect whether gravity behaves slightly differently at extremely small scales, a potential clue that extra dimensions might exist. Then there is another idea, even more abstract but deeply fascinating. It suggests that every mathematically possible universe might actually exist. This concept, sometimes called the mathematical universe hypothesis, proposes that reality itself may simply be a structure defined by mathematics. If a set of mathematical rules can describe a consistent universe, then that universe might exist somewhere within the greater landscape of possible realities. In this view, our universe is just one mathematical structure among countless others. Some universes might have 3 spatial dimensions like ours. Others might have 4, 5, or even more. Some might have completely different physical laws governing how particles interact. Most of these universes would likely be chaotic or short-lived. But a few might produce stable galaxies, long-lived stars, and planets where life could slowly emerge. These ideas stretch far beyond our everyday intuition. Yet they arise from serious attempts to understand the deepest laws of physics. And perhaps that is one of the most beautiful aspects of scientific exploration. When scientists follow the logic of nature carefully enough, they sometimes arrive at possibilities that feel almost poetic. Possibilities that suggest reality may be richer, stranger, and more layered than we once believed. Of course, these ideas remain speculative. At the moment, we have no direct evidence that other universes exist. Our observations are limited to the observable universe, the region of space from which light has had time to reach us since the beginning of cosmic history. Even that region is unimaginably vast. Within it, there are more galaxies than grains of sand on many beaches of Earth. Each galaxy contains billions of stars, and many of those stars are surrounded by planets. Already, this observable universe provides more than enough wonder to fill a lifetime of discovery. But the idea that it might be only one small part of something even greater continues to inspire scientists and dreamers alike. It reminds us that the cosmos still holds many secrets, that our understanding of reality is still unfolding, and that somewhere beyond the horizon of what we can currently observe, the universe, or perhaps many universes, may continue quietly expanding, forming new stars, new galaxies, and new possibilities. As we explore these ideas tonight, we are not just imagining distant worlds. We are gently touching the edges of one of the deepest questions science can ask. How big is reality, truly? And could it be far larger than we have ever dared to imagine? As we continue exploring these ideas, it helps to remember something quietly humbling. The universe that we can actually see, the observable universe, is only a small portion of what may exist. Light travels at an incredible speed, about 300,000 kilometers per second. Even at that speed, light takes time to cross the immense distances between stars and galaxies. Because the universe itself began around 13.8 billion years ago, there is a limit to how far light has had time to travel. That limit creates a kind of cosmic horizon. Everything beyond that horizon may still exist, but we cannot see it yet because its light has not had enough time to reach us. And the observable universe already stretches nearly 93 billion light-years across. Within that enormous sphere of space, astronomers estimate there may be 2 trillion galaxies, each filled with billions of stars. It is already an almost unimaginable scale. Yet even that vast region may be only a small island within something far larger. Some cosmologists believe that space could extend far beyond the observable universe, perhaps infinitely. If the laws of physics are similar across that larger expanse, then distant regions of space may contain their own galaxies, stars, and planets just like ours. In an infinite universe, something remarkable begins to happen. If matter is distributed randomly across endless space, then eventually certain patterns will repeat. Given enough distance, the arrangement of atoms that forms our own galaxy might appear again somewhere else. With even greater distance, the arrangement of atoms that forms our own solar system might repeat. And in the farthest reaches of an infinite cosmos, there could even be regions where atoms assemble into planets nearly identical to Earth. This idea does not require different physical laws or exotic dimensions. It simply arises from the mathematics of infinity. If space truly extends without limit, then somewhere in that vastness, countless variations of cosmic history could exist. Worlds similar to ours. Worlds very different from ours. entire cosmic neighborhoods unfolding along slightly different paths. Of course, such places would be unimaginably far away, or far beyond any possible travel. Yet the thought itself invites a quiet sense of wonder. Reality may be far richer than the small region we are able to observe. Meanwhile, physicists studying the earliest moments of the universe have discovered something else intriguing. The universe we see today contains tiny irregularities in its structure, faint patterns left behind from the earliest moments after the Big Bang. These patterns are visible in the cosmic microwave background, a faint glow of radiation that fills the entire sky. This radiation is the afterglow of the early universe, a snapshot of the cosmos when it was only about 380,000 years old. Within that ancient light, scientists have found extremely subtle fluctuations in temperature. Tiny variations that later grew into the galaxies and clusters we see today. These fluctuations are believed to have originated from quantum fluctuations, microscopic uncertainties that existed in the earliest moments of cosmic inflation. In other words, the entire large-scale structure of the universe, the galaxies, the stars, the planets, may ultimately trace back to tiny quantum ripples in the fabric of space. And if inflation occurred in many places across a much larger cosmic landscape, those quantum fluctuations may have produced countless universes, each with slightly different starting conditions. Some universes might expand rapidly. Others might collapse quickly. Some might never form galaxies at all. But a few, perhaps like ours, might settle into stable cosmic structures where stars shine for billions of years and planets slowly form around them. On some of those planets, life might emerge. And on rare worlds, that life might eventually begin to ask questions about the nature of the universe itself. It is a strange and beautiful thought. Across a vast cosmic landscape filled with many universes, there may be countless observers scattered across space and time. Each one looking outward. Each one wondering how reality truly works. Perhaps on some distant world, another civilization has already begun asking the same questions we are exploring tonight. Perhaps their scientists have also studied the earliest light of their universe, searching for clues about whether other universes exist beyond their cosmic horizon. Or perhaps they too sit quietly beneath their night sky, watching the stars drift slowly overhead and wondering whether their universe is the only one. In the end, the idea of parallel universes may remain uncertain for a long time. But even the possibility invites us to think more deeply about the nature of reality. It reminds us that the universe, and perhaps the multiverse, may be far larger, stranger, and more mysterious than our current understanding can fully grasp. And as science continues to explore these questions, one quiet truth remains. The deeper we look into the cosmos, the more beautiful and surprising it becomes. And as these ideas unfold, another quiet question begins to appear. If parallel universes truly exist, could they ever interact with our own? At first, most physicists assumed that separate universes would be completely isolated. Each one would expand within its own region of space, separated by enormous distances or hidden dimensions. From inside our universe, we would never notice the others. But some theories suggest that under certain conditions, universes might leave faint traces of their existence. One possibility comes from the earliest moments after the birth of our universe. If many universes formed during cosmic inflation, expanding like bubbles in an enormous cosmic ocean, then occasionally two expanding bubbles might have collided with one another. Such collisions would have happened when the universes were extremely young, long before galaxies or stars existed. If our universe experienced such a collision early in its history, the event might have left subtle patterns in the cosmic microwave background, the faint radiation that fills space and carries the imprint of the early universe. Astronomers have carefully studied this ancient light, looking for unusual circular patterns or distortions that might hint at a collision with another universe long ago. So far, the evidence remains uncertain. But the fact that scientists are even able to search for such clues shows how far our understanding of the cosmos has come. Another possibility emerges from the strange behavior of quantum physics. At the smallest scales, the universe does not behave like the familiar world we experience every day. Instead of definite positions and clear outcomes, particles exist in clouds of probability. They can occupy multiple possible states at once until a measurement is made. Some interpretations of quantum mechanics suggest that every possible outcome of a quantum event actually occurs, each outcome unfolding in its own branch of reality. In this view, reality is constantly branching into countless parallel histories. Every decision, every random event, every quantum interaction could lead to new branches of the universe quietly splitting away from one another. These branches would not exist somewhere far away in space. Instead, they would exist alongside our own, sharing the same origin but diverging through different possibilities. In one branch, a particle moves one direction. In another, it moves somewhere else. Over time, these tiny differences might grow larger, shaping entirely different histories of events. Yet these parallel branches would remain hidden from one another. Once they diverge, they no longer interact. Each branch would feel like a complete and self-contained universe to the observers living within it. Another fascinating area of research involves something called quantum entanglement. When two particles become entangled, their properties become linked in a strange way. Even if the particles are separated by enormous distances, measuring one instantly determines the state of the other. This phenomenon puzzled scientists for decades, because it seems to create a connection between distant particles faster than light could travel. While entanglement does not allow information to move faster than light, it does reveal something profound about the nature of reality. The universe may be far more interconnected than our everyday intuition suggests. Some physicists have even proposed that the fabric of space itself might emerge from networks of entangled particles. In other words, the geometry of the universe, the structure of space and time, may arise from deeper quantum relationships linking everything together. If this idea is true, then the boundaries between universes might not be as simple as separate bubbles drifting in empty space. Instead, the deeper structure of reality might resemble a vast interconnected web of quantum information. Another intriguing thought arises when we consider the future. If the multiverse exists, then universes may continue forming far into the distant future. Cosmic inflation may still be occurring in regions far beyond our observable horizon, quietly generating new universes as space continues to expand. Each new universe might begin with its own Big Bang, developing galaxies, stars, and planets over billions of years. Across this immense cosmic landscape, countless universes may be unfolding simultaneously. Some young, some ancient, some expanding rapidly, others collapsing or evolving in entirely different ways. And somewhere within that vast multiverse, there may be worlds where life has emerged in forms completely unfamiliar to us. Creatures evolving under different stars. Civilizations shaped by different histories. Observers asking questions about their own universe, wondering whether reality extends beyond what they can see. In the quiet of the night sky, these ideas remind us of something both humbling and beautiful. Our universe, immense as it is, may not be the entire story. It may simply be one chapter within a much larger cosmic book. And as science continues exploring the deepest laws of nature, we slowly turn the pages of that story, discovering new mysteries, new possibilities, and new ways of understanding the universe we call home. As physicists continue to explore the mathematics behind these ideas, something fascinating began to emerge. The concept of parallel universes was not invented simply for imagination or storytelling. In many cases, it appeared naturally while scientists were trying to understand the deepest laws of nature. One of the most famous examples comes from a theory called string theory. String theory attempts to describe all particles and forces in the universe using a single underlying framework. In this model, the tiny particles that make up matter are not point-like dots, but extremely small vibrating strings of energy. Each vibration pattern corresponds to a different particle, electrons, quarks, photons, and other fundamental components of matter. But when physicists began working through the equations of string theory, they discovered something surprising. The theory did not describe only one possible universe. Instead, the mathematics allowed for an enormous number of possible universes, each with slightly different physical properties. The way extra dimensions fold or twist within the theory can produce different sets of physical laws. Some versions of these universes might contain stable atoms and long-lived stars. Others might collapse almost instantly or behave in ways that would make life impossible. This idea became known as the string theory landscape. According to some estimates, there could be as many as 10 possible universes allowed by the equations of string theory. That number is so large that it is difficult to comprehend. It is far greater than the number of atoms in the observable universe. Within such a vast landscape of possibilities, our universe might simply be one region where the laws of physics happen to allow complex structures like galaxies and living organisms to form. Another interesting fact about the multiverse idea is that it can sometimes help explain certain puzzles in cosmology. For example, our universe appears to be expanding at an accelerating rate. This acceleration is believed to be caused by something called dark energy, a mysterious form of energy that fills empty space and pushes galaxies apart. One of the biggest mysteries in physics is why dark energy has the value that we observe. If it were slightly stronger, galaxies might never have formed. If it were slightly weaker, the universe might have collapsed long ago. In a multiverse, however, this strange balance might simply be one possibility among many. Different universes could have different amounts of dark energy. Only those with the right conditions would develop long-lived galaxies and stars, allowing observers like us to exist and measure them. Another fascinating observation comes from the structure of the universe itself. When astronomers map the positions of galaxies across enormous distances, they find that galaxies are not distributed randomly. Instead, they form an intricate pattern often called the cosmic web. Massive filaments of galaxies stretch across hundreds of millions of light-years, connecting clusters of galaxies like threads in a giant three-dimensional network. Between these filaments lie vast regions of almost empty space known as cosmic voids. This structure formed over billions of years as gravity slowly pulled matter together from tiny fluctuations in the early universe. But the patterns we see today may also contain clues about the conditions present at the moment the universe began. Some scientists continue to study these large-scale structures carefully, hoping to learn whether they might reveal hints about inflation or even the presence of other universes beyond our cosmic horizon. Meanwhile, advances in telescope technology continue to expand our view of the cosmos. Modern instruments such as the James Webb Space Telescope allow astronomers to observe galaxies that formed when the universe was only a few 100 million years old. These distant galaxies appear faint and red because their light has traveled across billions of years of expanding space. By studying these ancient objects, scientists are learning more about how the first stars and galaxies formed. And each new observation helps refine our understanding of how the universe evolved from its earliest moments to the vast cosmic landscape we see today. Interestingly, the idea of multiple universes also appears in another area of theoretical physics called eternal inflation. According to this model, the process of cosmic inflation may never fully stop. Instead, inflation continues in some regions of space while ending in others. Each region where inflation stops becomes a new universe with its own Big Bang. If this process has been happening for billions or even trillions of years, then the number of universes could be unimaginably large. Some universes might be extremely young, just beginning their cosmic evolution. Others might be incredibly ancient, having already passed through billions of years of stellar formation and galactic development. The multiverse, in this sense, would resemble an enormous cosmic landscape filled with universes at different stages of their existence. Of course, it is important to remember that many of these ideas remain theoretical. Science relies on observations and experiments, and the multiverse, if it exists, may be extremely difficult to test directly. Because other universes might lie beyond the limits of our observable horizon, they could remain permanently out of reach. Yet scientists continue exploring these ideas because they arise naturally from our best attempts to understand the fundamental laws of nature. And even if the multiverse remains uncertain, the exploration itself leads to deeper insights about space, time, and the structure of reality. The story of science is filled with moments when bold ideas eventually led to unexpected discoveries. Centuries ago, the idea that Earth orbits the Sun seemed radical. Later, the discovery of other galaxies revealed that the Milky Way was only one among billions. Today, the possibility of parallel universes may represent the next step in that long journey of discovery. A reminder that the universe, and perhaps the multiverse, may still hold many secrets waiting quietly beyond the horizon of what we can currently see. As scientists continued exploring the mathematics of the universe, another curious realization slowly began to emerge. The laws of physics that govern our world appear to be surprisingly simple, at least in their basic form. With only a handful of fundamental forces and a small set of physical constants, the universe has been able to produce stars, galaxies, planets, and eventually living organisms capable of studying the cosmos itself. Yet many physicists have wondered why these laws take the exact form that they do. Why do the strengths of the fundamental forces fall within the narrow ranges that allow stable atoms to exist? Why do particles have the particular masses we observe? Why does space have 3 large dimensions instead of 4 or 5? In a single universe picture, these numbers can seem almost mysterious, as if the universe were somehow finely balanced. But within the framework of a multiverse, this balance may arise naturally. If many universes exist, each with slightly different physical constants, then most of them would likely be chaotic or short-lived. Stars might never form. Matter might collapse too quickly or drift apart too rapidly. Only a small fraction of universes would develop the stable conditions necessary for galaxies and planets to emerge. In those rare universes, complex chemistry could occur. And within that chemistry, life might eventually appear. This line of reasoning is sometimes referred to as the anthropic principle. It suggests that the universe appears finely tuned for life because observers can only exist in universes where such conditions are possible. Another interesting fact about parallel universe theories is that they often arise when scientists attempt to combine two of the most successful theories in physics, general relativity and quantum mechanics. General relativity describes gravity and the large-scale structure of space and time. It explains the motion of planets, the bending of light near massive objects, and the expansion of the universe itself. Quantum mechanics, on the other hand, describes the behavior of particles at the smallest scales, atoms, electrons, and the strange probabilistic world of subatomic interactions. Both theories work extremely well in their own domains. But when scientists try to apply them together, such as inside black holes or at the very beginning of the universe, the equations become extremely difficult to reconcile. This challenge has led physicists to explore new theoretical frameworks, including string theory, quantum gravity, and multiverse models. Some of these theories suggest that reality may have a much deeper structure than we currently understand. For example, certain models of quantum gravity propose that space itself may not be continuous. Instead, space might be made of tiny discrete units, unimaginably small building blocks that combine to form the geometry of the universe. If this is true, then space and time may emerge from an even deeper layer of physical reality. In some interpretations, that deeper layer might naturally produce many possible universes. Each one would represent a different arrangement of these fundamental building blocks. Another fascinating area of research involves cosmic topology, the large-scale shape of the universe. When we think about space, we usually imagine it extending endlessly in every direction. But mathematically, space could also have more complex shapes. For example, the universe might wrap around itself in ways similar to the surface of a sphere or the shape of a torus, sometimes compared to the geometry of a donut. In such a universe, traveling far enough in one direction might eventually bring you back to your starting point, even though space appears infinite from a local perspective. Studying the cosmic microwave background helps scientists search for patterns that might reveal the true geometry of space. So far, the universe appears to be extremely flat and vast, but the possibility of more complex shapes has not been completely ruled out. Meanwhile, the study of black holes has opened another window into the deeper structure of reality. Black holes form when massive stars collapse under their own gravity, compressing matter into incredibly dense regions where gravity becomes so strong that not even light can escape. For many years, physicists believed that information falling into a black hole might be permanently lost. But later research revealed something surprising. Black holes appear to possess entropy, a measure of the amount of information they contain. In fact, the entropy of a black hole is proportional not to its volume, but to the area of its event horizon, the boundary surrounding it. This discovery led to an idea known as the holographic principle. According to this concept, the information contained within a volume of space may actually be encoded on its boundary surface. In a sense, the universe itself might behave like a cosmic hologram, where the three-dimensional world we experience emerges from information stored on distant boundaries of space. Some physicists believe that this principle may eventually help unify gravity and quantum mechanics. And in certain models, the holographic principle may even allow for connections between different regions of space or different universes. Although these ideas remain deeply theoretical, they show how far scientists have pushed the boundaries of our understanding. The deeper we explore the laws of nature, the more we discover that reality may be layered with structures far beyond what we once imagined. What once seemed like science fiction, multiple universes, hidden dimensions, cosmic holograms, now appears in the mathematical frameworks physicists use to describe the fundamental workings of the cosmos. Yet even with all these theories, one thing remains clear. The universe still holds many mysteries. And as scientists continue studying the faint light of distant galaxies, the subtle ripples of gravitational waves, and the strange behavior of quantum particles, each new discovery brings us a little closer to understanding the true nature of reality. Whether our universe stands alone or is part of a vast multiverse, the search itself continues, quietly expanding our view of the cosmos with every new observation. And as these ideas continue to unfold, scientists often return to one simple but profound question. If other universes exist, could they ever leave traces that we might detect? While most multiverse theories suggest that other universes would be permanently separated from ours, a few intriguing possibilities remain. In the earliest moments after the birth of our universe, space expanded at an extraordinary rate during the period known as cosmic inflation. During that time, the universe was incredibly small, hot, and dense. If our universe formed as one expanding bubble among many, then in those first moments there might have been brief interactions between neighboring bubbles before they drifted apart. These collisions would have happened long before galaxies, stars, or planets existed. But in theory, they might have left subtle fingerprints in the structure of the universe itself. Astronomers have searched for such fingerprints in the cosmic microwave background, the faint radiation left over from the early universe. This ancient light acts almost like a photograph of the cosmos when it was still very young. By mapping the tiny variations in this radiation, scientists can study the earliest patterns that later grew into galaxies and clusters of galaxies. If our universe ever brushed against another universe during its infancy, it might have created unusual circular patterns or temperature variations within this ancient glow. So far, no clear evidence of such a collision has been confirmed. But the search itself continues, using ever more precise observations of the sky. Another fascinating idea involves the strange structure of black holes. Black holes are among the most extreme objects in the universe. When a massive star collapses, its gravity can compress matter so tightly that space and time themselves become severely distorted. At the center of a black hole lies a region known as the singularity, where our current theories of physics begin to break down. Some theoretical models suggest that the interior of a black hole might connect to another region of space-time, perhaps even forming a new universe. In this idea, the collapse of matter into a black hole could trigger the birth of a new expanding region of space beyond the event horizon. From inside that new region, the event might appear very similar to a Big Bang. If such processes occur, then every black hole in our universe might potentially give rise to a new universe of its own. Over time, universes could give birth to new universes through the formation of black holes, creating an enormous cosmic family tree stretching across unimaginable spans of time. This idea, sometimes called cosmic natural selection, even suggests that universes that produce many black holes might generate more offspring universes than those that do not. While this concept remains speculative, it shows how deeply scientists are willing to explore the consequences of known physical laws. Another curious observation about our universe is the remarkable uniformity of its large-scale structure. no matter where astronomers look across the observable cosmos, the laws of physics appear to behave the same way. The same types of atoms exist in distant galaxies. The same gravitational laws govern the motion of stars and planets. Light from distant galaxies, traveling billions of years through space, carries the same chemical fingerprints that we observe here on Earth. This consistency is one of the reasons scientists are able to study the universe so effectively. But it also raises an interesting possibility. If our universe is only one region within a much larger multiverse, then each universe might have its own internal consistency, its own stable laws of physics that remain constant across its own space. To observers within any given universe, the laws of nature would appear universal. Yet those laws might be different in other universes beyond the boundaries of our own. Meanwhile, modern telescopes continue pushing our observational limits further than ever before. The James Webb Space Telescope, for example, has begun observing galaxies that formed extremely early in cosmic history, some appearing less than 1 billion years after the Big Bang. These ancient galaxies help scientists understand how quickly stars formed and how the first structures of the universe emerged from the primordial gas left over from its birth. Each new observation helps refine our understanding of how the cosmos evolved. And each discovery reminds us that our picture of the universe is still incomplete. Perhaps someday, new experiments in quantum physics or new observations of the early universe will reveal clues that bring us closer to understanding whether parallel universes truly exist. Or perhaps the multiverse will remain one of the great mysteries, an idea suggested by the deepest mathematics of physics but forever beyond direct observation. Either way, the exploration of these possibilities has already changed the way we think about reality. It has shown us that the universe may be far larger, deeper, and more complex than we once believed. And that beyond the quiet glow of distant galaxies, the story of the cosmos may still be unfolding in ways we are only beginning to imagine. And as our journey through these ideas slowly comes to a close tonight, it helps to pause for a moment and take in the quiet scale of everything we have explored. The universe we live in already stretches beyond imagination. Billions of galaxies drift through space, each one containing billions of stars. Around many of those stars orbit planets, some frozen and silent, others perhaps warm enough for oceans and clouds to form. On one small planet, around one ordinary star, life appeared. Over millions of years it evolved, changed, adapted, and eventually gave rise to creatures capable of asking questions about the universe itself. And that is where we find ourselves tonight. A species that emerged from oceans and forests, now sitting quietly beneath the stars, wondering about the deepest structure of reality. The idea of parallel universes invites us to imagine that our universe might not be the only one. Perhaps beyond the horizon of what we can see, countless other universes exist, each with its own galaxies, its own stars, its own histories unfolding in distant cosmic silence. Some of those universes might look very similar to our own. Others might be wildly different, shaped by physical laws we cannot yet imagine. And perhaps in a few of them, life has also appeared. Maybe there are worlds where distant civilizations gaze upward at their own night skies, studying the faint glow of their galaxies and wondering about the same questions we ask tonight. Are we alone? How large is reality? What lies beyond the limits of what we can observe? These questions have guided human curiosity for centuries, and they will likely continue guiding it for many centuries to come. Science does not always provide immediate answers. Often, it offers something quieter and more beautiful. It gives us ways to explore the unknown, to ask deeper questions, and to slowly expand our understanding of the universe we inhabit. Every new telescope, every spacecraft, every experiment pushes the boundaries of what we know just a little further outward. And with each discovery, the universe becomes both more understandable and more mysterious at the same time. That quiet balance between knowledge and wonder is what keeps exploration alive. So as you relax and let your thoughts drift gently like distant galaxies, imagine the immense cosmic ocean surrounding us. Vast regions of space stretching far beyond our view. Stars forming, shining, and fading across billions of years. Planets circling quietly in the darkness. And perhaps, scattered among those distant worlds, other minds slowly awakening to the same curiosity we feel. For now, we remain observers within our small corner of the cosmos. But our understanding continues to grow. And the universe, patient and ancient, continues unfolding its story. So rest now, and let the quiet beauty of the cosmos settle around you. The stars will still be there when morning comes. And somewhere in the deep silence between them, the mysteries of the universe continue waiting, calm, vast, and full of possibility.